like to thank the Anusandhan National Research Foundation for supporting my travel here. So this lecture is going to be about noise processes in pulsar timing arrays. Uh, and that is the official mascot of PTO noise analysis. You would have seen that in many places. And this is sort of a summary slide of what I'm going to talk about. The goal here is to sort of look under that mask and see what is hiding there. So, yeah. Okay. Okay. So let me give you a quick recap of pulsar timing arrays or pulsar timing and or how a TOA is made. That's because the data in a pulsar timing array are essentially times of arrival of pulses. And to be able to do noise analysis or noise characterization of such a data set, we need to understand how this thing is made. So the bottom plot is a cartoon of what happens when a pulsar emits a pulse. So the pulsar is going around a binary companion, and as it rotates, it will emit radio pulses, which travels through the interstellar medium and reaches Earth, which is rotating and going around the sun. So so the relative position between the pulsar and the Earth keeps changing, which means that the propagation time between the pulsar and the Earth is a function of time. Also, it passes through the interstellar medium, which has some finite frequency dependent refractive index. So that also contributes to the light travel time between the pulsar and the Earth. And so the time at which we actually measure this pulse at our observatory is the time of emission at the pulsar plus this propagation time. And in addition to that, once the pulse reaches our telescope, it is not immediately recorded. It has to go through this observatory electronics and computer that is actually doing the data reduction and recording, etc. And so that process has some finite amount of delay, and that is also included in the time of arrival that is actually recorded. And also this time that we are actually recording is not referenced against some kind of universal time. It is referenced against a clock that is there in the observatory. And so if that clock is not very good, then that will reflect. And if that clock against which we are recording this times of arrival is not good, then our measurements will only be as good as that. So once we have once we have recorded our data, this is sort of how we make a TOA out of that. So the actual observation, the actual output of the telescope is originally what is known as baseband data, which are voltages induced by the incident radio wave, which we reduce to a frequency resolved light curve by doing a windowed Fourier transform. And the aim here is to reduce the size of the data so that we can work with it easier. But still, to measure a TOA, we have to fold this data to obtain what is known as an integrated pulse profile. And then we measure a TOA or multiple TOAs from this integrated pulse profile by matching it against a template. So our measured TOA is in fact a resultant of all these processes that are, so all these astrophysical processes, all of those processes happening inside that the observatory hardware, and all of these things happening in software. So our observed TOA is a sum of all of this. So the whatever noise model that we are using has to reflect all of these things accurately. So let me now come back to what an PTA experiment does actually. So it takes these measurements of TOAs from multiple pulsars and to find gravitational wave signatures in them, which are which you will hear in later lectures, are signals that are correlated across multiple pulsars. So as I said before, the measured TOAs are not just they don't just contain the gravitational waves. They contain a large number of astrophysical and instrumental effects other than the gravitational waves. And in order to find the gravitational waves, we have to model all of these effects adequately to detect gravitational waves. And so to do this, we define a mathematical object called a timing and noise model. It is a mathematical description of all of these processes together. So I am talking about this as a singular entity because in sometimes in usual practice we talk about timing model and noise model as being different things, but strictly speaking, physically they are not. There is a single timing and noise model which we may treat as split into different things for convenience or computational reasons, but mathematically speaking, that is a single entity. And a timing residual is the difference between a measured TOA minus that whatever is predicted by the model. So, my definition of noise here is that the noise is any effect influencing a TOA other than what we are currently trying to detect or study. So let me give you an example. So this is my scenario 1, where I am trying to detect individual gravitational waves. So all of these things in red is noise in this case. Only the blue thing is my signal. And if in scenario 2, if I am trying to test general relativity, only the pulsar binary motion is my signal. Everything else is noise. So this is something we have to keep in mind whenever we are trying to do pulsar timing array noise characterization, because this ultimately the sensitivity of our experiment not only depends on things that we usually think of as noise. It also depends on all of these things taken together. So it is very important to keep this in mind. So we can classify these noise processes. By noise, I mean all of those things together in multiple different ways. So some of them are astrophysical versus instrumental. So this is not really of any practical interest because we don't really care when we are doing computation what is astrophysical versus what is an instrumental. But when you are doing science, this is important. So the more important category is pulsar correlated versus pulsar uncorrelated. This is extremely important because the signal that we are trying to detect, the gravitational waves, are pulsar correlated. And so so the other signals that are pulsar correlated are especially harmful when we are trying to detect gravitational waves. So there are also signals that are time correlated versus time uncorrelated. There are signals that are achromatic versus chromatic. So this is achromatic versus this distinction is about the dependence on radio frequency. So some signals are purely kinematic. Things like the rotation of the pulsar, they are purely kinematic effects and they don't really depend on the observing frequency of your telescope. But there are some other effects, things like the dispersion in the interstellar medium, which depends on the radio frequency of your observation. So that is what this distinction is. Achromatic means independent of frequency, and chromatic means depends on observing frequency. And sometimes some of these quote unquote achromatic signals, or rather signals that we used to treat as achromatic, may in fact turn out to be chromatic. So a recent example for this is pulse jitter, where recent studies have shown that pulse jitter actually has a frequency dependence.
There is also deterministic versus stochastic. This distinction is really arbitrary. So it is very, very subjective what you treat as deterministic versus what you treat as stochastic. And most of the time, this has to do with the conventions of your model or computational convenience or whatever. So so an example of this arbitrariness is solar wind. So if you have a very, very accurate measurements of solar wind using, say, interplanetary scintillation or something, then you can subtract out the solar wind. And so that is a deterministic signal because you know what the solar wind is doing. But if you don't have that information, you usually model this as something like a Gaussian process or something, which is a stochastic signal. So this distinction between deterministic and stochastic is really not physical. It is arbitrary. Okay, so there are four ways in which we can deal with noise processes in pulsar timing arrays. The first is, in some cases, we can simply remove the noise affected parts of the data. So some types of noise are really sort of localized in some sense. For example, an example would be radio frequency interference. So many of the radio frequency interference, for example, those caused by satellites or mobile phones, those exist in certain definite radio frequency bands. And if we know what to look for, we can just cut out that part. And so we can just get rid of it even before calculating any TOAs. So we are good with that. The second way is if we can sort of measure this process very accurately or measure some aspect of that process very accurately, then we can directly use that information in pulsar timing. So an example of this would be observatory clock corrections. So in most of the time, we can actually independently measure the observatory clock corrections between your observatory clock and some international time standard very accurately. And usually what is done is you just subtract out that correction from your TOA so that when you actually do the timing, you don't have to worry about that particular thing. Another thing is Earth's rotational history, which is also corrected for when you do timing before doing any fitting or anything. Another example would be solar system ephemerides, which determine what your solar system motion delays would be, and so on. But there is no guarantee that these measurements are 100% accurate. So if you use an inaccurate measurement for this kind of purpose, then there will be errors in your these errors will show up as some residual noise in your data, which you have to again take care afterwards. There are the third category is where we don't have any information about independent information at all. So this is, for example, things like spin, the rotation of the pulsar or interstellar medium. In this kind of cases, we don't know anything other than what the pulsar observation is telling us. So in this case, we have to model it together with whatever we are actually trying to measure. And finally, in some cases, we may have some information, but not very precise information. So in that case, we still have to treat them treat those signals together with whatever we are trying to measure. But we can use that information as sort of Bayesian priors when we are doing Bayesian analysis. Examples for this would be things like VLBA astrometric measurements, or if we have like independent optical or infrared measurements of pulsar binary system or things like that. So this first and second categories we don't encounter really when we are doing what we usually think of as pulsar noise analysis, because they have already been taken care in previous steps along the way. But if these items 1 and 2 have not been done accurately, it will show up in your noise analysis and you have to deal with them. So, and this is something we have to be very, very careful about. Okay. So now let's come to this distinction between noise timing model and noise model. So this is this is done very frequently. In fact, most of pulsar timing array analysis is done this way because it is convenient to do this. So when we are actually doing this in practice, like treating everything together at all the time is very difficult and also computationally expensive. So what we do is that we split the timing and noise model into one chunk which contains all the big effects, and one chunk that are sort of perturbations to the big effects. So the big effects are together called the timing model, and big in this context basically means that the effect of these effects on the TOAs is comparable to or greater than the pulsar rotational period. So an example for this would be solar system Romer delay. So that is of the order of 8 minutes, which is much greater than the period of any millisecond pulsar, which are of the order of milliseconds. So what we do in practice is that we do take care of all of these big effects when we are doing timing, and then we calculate the timing residuals using the sort of approximate timing model while neglecting the other small effects. So the examples for this would be spin down solar system motion, binary motion, large scale trends in interstellar dispersion, things of that nature. Then our noise model is whatever is left, or rather whatever is left after we take care of the big effects. This includes small deviations in the big effects, which is the timing model, plus all the everything else. So small in this case again means that the effect on the TOA is much smaller than the pulsar rotation period, and it turns out that these effects can be treated as linear perturbations on the TOAs. So and these basically manifest as non-zero timing residuals. So the advantage here is that if we do this splitting carefully and correctly and accurately, then we don't have to do this full analysis anymore. We just can do with a linearized version of the timing model, which is much easier to deal with computationally. So the examples for these small effects are radiometer noise, pulse jitter, dispersion variations, which are variations on top of these large scale trends, spin noise, etc. Which spin noise is basically small deviations in the pulsar frequency on top of the big spin down effect. But it is always important to keep in mind that this separation is always arbitrary and model dependent. So in some model, some parts of these things may be taken as part of timing model or vice versa. So there is no clear line where we see that this is part of timing model and this is part of noise model. So it is all pretty arbitrary and model dependent, and the way we choose how we do this is mostly based on computational considerations or just convenience. So okay, so now I will come to components of the noise model, which are those small effects that I mentioned. So this is basically what we think of as when we talk about noise analysis. So before we start, let me give you a very hand-wavy definition of a Gaussian process, because a lot of these processes are treated as Gaussian processes in noise analysis. So let's say we have a stochastic signal y given by some y0 plus tb, where t is some rectangular matrix and b is some parameter vector. And if we assume that this vector b has a probability distribution which is normal with a zero mean and some covariance matrix b, then we can call this process y as a Gaussian process. So for PTA applications, we usually choose this matrix B. T is called a basis matrix, and we choose T such that the dimensionality of that vector B is much less than the dimensionality of that vector Y. So this is also known as a reduced rank representation, and the advantage here is that all the matrix operations that we have to do to to do the data analysis become much more computationally tractable. So this is in no way a mathematically rigorous definition, but this will do for our purposes. Okay, so now coming back to different noise processes, the sort of most vanilla noise process or the simplest noise process is the radiometer noise. So this is the combination of the noise introduced by the electronics that is inside in your observatory, plus all the other sources in the sky, radio sources in the sky that the telescope is seeing. So this latter thing is called sky background, but there is no real way to distinguish between the two. It is colloquially also known as white noise. And is there a problem? Okay. Okay. Anyway, so this is time uncorrelated and pulsar uncorrelated and achromatic. So that basically just means that it has no frequency dependence, and it has no time dependence, and it also does not really care about what pulsar you are looking at. Oh, okay. Okay, yeah. But it is part in part produced by your observing the telescope electronics. So it depends on your observing system and its settings. And an estimate of the radiometer noise of each TOA, we can get that by taking the measurement uncertainty sigma, which comes for each TOA observation. But this sigma may or may not be accurate. It can be inaccurate due to various reasons, including imperfections in your TOA measurement procedure. If your polarization calibration is off, that can affect your uncertainty estimate. If you have a radio frequency interference that you have not successfully removed, that can also affect the uncertainty estimate. So usually what we do is that we sort of modify that uncertainty estimate sigma by sort of scaling and shifting it using two parameters called EFAC and EQUAD. EFAC just means error factor, and EQUAD means error added in quadrature. So these are just fudge factors to sort of make sure that this sigma is realistic. So this is what pure radiometer looks like in a pulsar observation. It just looks like some white noise without any pattern. So the second type of noise I will talk about is pulse jitter. So this actually has an astrophysical origin, unlike the radiometer noise. So this originates because of the fact that each pulse emitted by the pulsar has some random shape. But if we take a very large number, or rather an infinite number of pulses, and average them together to form a integrated pulse profile, the integrated pulse profile will have a stable shape, but individual pulses have varying shapes. So but in practice, what we actually do is that we only take in any observation we can only take a finite number of pulses. So since each pulse has some random variation, when we integrate our observation over some n, however large that may be, we will still have some residual some residual randomness in the shape of our pulse, and that is known as pulse jitter. So one important property of the pulse jitter is that if we take all the different frequency channels from the same observation, then the pulse jitter in all of these channels will be correlated. So that means that it is it is not correlated across different observations, but it is correlated within the same observation. So, and traditionally, this has been treated as sort of achromatic, as in it has as without any frequency dependence. But recent studies have shown that it in fact has some frequency dependence. So that what that means is that we have improved models of pulse jitter to really characterize it better. Uh, it also turns out that the pulse jitter somehow partly depends on the observing system and its settings. That is because your observation is affected by the telescope band pass and things like that. And this is represented by the E-quad, which appeared in the previous slide also, and as well as another parameter called an E-core. So what E-quad does is that it introduces some extra uncertainty in your TO for your TOAs. And what E-core does is that it introduces a correlation between TOAs measured from the same observation. There have been some advances in this area. So recently, people have proposed some profile domain techniques to get rid of or to mitigate pulse jitter, so that so that we don't have to deal with this when we are analyzing TOAs. So, but all that is still in sort of development stage. The standard way of dealing with jitter is to model it simultaneously with other types of noise. So now I come to spin noise, which is slow stochastic wandering of the pulsar rotational frequency. So the pulsar rotates, and as it emits electromagnetic as well as possibly gravitational waves, it will spin down in time. But on top of that, it is believed that the internal dynamics, or rather whatever superfluid or superconducting material is inside the neutron star, has some dynamics of its own, and that dynamics can cause random variations. Small random variations in the pulsar's rotational frequency, and this is known as spin noise. So this is a purely kinematic effect. So it's time correlated, but it is not correlated across pulsars, and it has no chromatic dependence. It also does not depend on the observing system because it's a purely pulsar intrinsic noise, and it is often described as a Fourier domain Gaussian process with a power law spectrum. So I will not go into this math below. So this F represents the basis matrix. So that's a Fourier basis, sines and cosines. And that phi basically represents the spectrum of this process. So it is usually treated as some kind of a power law or a broken power law or a power law with some kind of plateau or something like that. So this is what spin noise looks like. This is very strong spin noise, but this is what spin noise looks like in timing residuals. You would see the sort of slow wandering of these TOAs, which are sort of correlated across time. Now, the next thing is dispersion noise. So these things happen due to variations in the interstellar dispersion measure, which is due to two things. One, the ISM itself is a dynamical entity, so it keeps changing with time slowly. The second thing is that both the Earth and the pulsar are moving with respect to each other, both due to solar system motion, binary motion, and also due to the sort of proper motion as well as galactic motion, and so on. So the line of sight between the Earth and the pulsar is not actually seeing the same part of the interstellar medium all the time. So due to these two reasons, we will see variations in the observed electron column density along our line of sight, and that manifests as what is known as the interstellar dispersion noise. So this is time correlated, but pulsar uncorrelated, because because pulsars are located at different parts of the sky, and different parts of the interstellar medium don't really talk to each other. So this is pulsar uncorrelated. And it is chromatic with a nu to the -2 dependence, where nu is the observing frequency. It also does not depend on your observing system, because it's an astrophysical process. And until very recently, it has been usually represented as a piecewise constant model called DMX. But more recently, people have started using a Fourier domain Gaussian process model similar to the spin noise called DMGP. One good thing about this is that, unlike radio, gamma ray observations of pulsars are not affected by interstellar dispersion. So if we combine our radio observations with gamma ray observations, we can characterize this very, very well. We cannot get rid of it, but we can characterize it much, much better. So this is what dispersion noise looks like in your observations. So these different colors represent different frequency bands. And as you can see that this yellow and green are lower frequency. So they are affected much more than the blue, which is at a slightly higher frequency. Yeah. 2 minutes? Oh. Okay. Okay. So the next thing is solar wind noise, which is due to variable solar wind. And it appears as those kind of spikes in your dispersion measure. And this is pulsar correlate. This is time, both correlated in time as well as pulsar, but it is very difficult to model the actual pulsar correlation of this. So people have not yet actually tried to, or rather succeeded in modeling it, modeling the pulsar correlation of this. And this is sometimes represented as a Fourier domain Gaussian process, similar to DM noise and all. But in my opinion, not a good model for various reasons. Let me take 10 minutes. It turns out we can actually do independent measurements of this using interplanetary scintillation. And some people here are doing that. And we can at least partly correct this using interplanetary scintillation measurements, which is nice. The next is scattering noise, which in my opinion is the nastiest form of noise in pulsar timing arrays. So these are caused by density fluctuations in the interstellar medium, which causes radio waves to undergo multipath propagation. In terms of timing, what that does is that it changes the observed pulse shape. So as you can see in that plot, the sort of higher frequencies get sort of distorted less, but lower frequencies are distorted much more, or smeared in sort of time and phase. So this kind of manifests as a chromatic process with some nu to the minus alpha dependence, depending on alpha, where alpha depends on the properties of the interstellar medium that we are talking about. But it is also uncorrelated between pulsars, because again, interstellar medium does not really talk to each other for different lines of sight. Unfortunately, we don't really have any good models for this type of noise. Everything, all we do to deal with this is ad hoc and hand wavy. But there are some promising directions. There are people doing cyclic spectroscopy, which gets rid of this altogether in the baseband domain, which is the best thing we can do. And there is things like clean algorithm, which is taken from imaging, I think. So this actually removes scattering in the profile domain. So this clean thing algorithm is less accurate, but if we don't have baseband data, then that's all we can do. But in any case, the takeaway from this is that it is probably not a good idea to try to deal with this in the TOA domain, but much better to get rid of it before we calculate the TOAs. Okay, so this is something people don't really talk about that often. This is binary orbital noise. So in some pulsars, we will have, especially for redback and black widow systems, where the pulsar has complex gravitational interactions with its companion. we can have the binary orbit will not be a Keplerian orbit, or it will not be, even be a sort of precessing or a shrinking Keplerian orbit. It may have some stochastic variations in it. It is not common in PTA pulsars because we don't usually throw away such pulsars while doing PTAs. But some pulsars have this type of variations, and that you can see by looking at the power files. If you see an ungodly number of FB parameters, this is what is going on. So this is achromatic, time correlated, and pulsar uncorrelated because binary is separate for each pulsar. And it does not depend on the astro observing system because it's pulsar dependent. It's a astrophysical process. And people have proposed piecewise constant as well as Fourier Gaussian process models, but these have not been adopted in PTA analysis as far as I can tell. And if we want to keep these pulsars, I think we have to like do much better. So this is, and the next thing is solar system ephemeris noise. This is what happens when the solar system ephemeris that we use to describe the orbital motion of the Earth is not accurate. So this is one of those residual noise processes that I was mentioning earlier. And this has a pulsar correlation because it's not really dependent on the pulsar, it's the motion of the Earth. So it affects every pulsar, but it has a sort of dipolar signature. And it is achromatic because it's a kinematic thing. So it can either be modeled as a deterministic signal or as a Gaussian process, depending on circumstances. But fortunately, our solar system ephemerides have gotten much better as compared to say 5 or 6 years ago. So now this is much less of an issue. The next thing is instrumental noise. It is clock noise. So if your TOAs are only as good as the clock against which it is measured. So if your clock is doing something weird, then you would see noise in your data. And that is this, and it will affect every pulsar equally. And so that is what is meant by a monopolar pulsar correlation. It has no frequency dependence unless your different frequency backends have some kind of issue. And again, it is maybe modeled as a deterministic signal or as a Gaussian process on a case-by-case basis, I think. Again, this has not been that prominent yet, but a clock issue can happen anytime. So it's a electronics instrument. So we can't really tell when this will pop up. Finally, the gravitational wave background is a noise if you are trying to do something other than gravitational wave background. So it is a time correlated and pulsar correlated and achromatic signal. So the pulsar correlation has a quadrupolar signature, or the Herlingson-Downs correlation. So you will hear much more about this in the upcoming lectures. So finally, the timing model deviations. So this is an extremely important part of the noise modeling process, because the initial timing, where we only took care of the big effects, is not 100% accurate because we have neglected all the small effects. So when we also include the small effects, the parameters of the original timing model will have to change to accommodate these new processes. So that has its own signature. And the biggest effects in this are the unknown overall phase offset, the rotational frequency and its derivatives, this unknown sky location and the parallax, which can be improved by including VLBI measurements, and unknown binary parameters if the binary orbital frequency is within the PTA band. Some pulsars have this property. And this is usually modeled as a Gaussian process with infinite prior variances, because we assume that we now don't know nothing about these processes a priori. So that's reflected in this infinite prior variances. And all of this can be, for every PTA, can sort of be summarized as a sensitivity curve. So this sort of represents the level of noise in a pulsar timing array experiment. So as you can see, it sort of looks like a bucket with two spikes. The low frequency part where it goes up is determined by the unknown frequency and its frequency derivatives as well as spin noise. The high frequency rising part is determined by pulse jitter and radiometer noise. And that one the big spike is at 1 year. That comes because of the unknown sky location. Unknown sky locations, we can get rid of it by including VLBI measurements or whatever. That small spike is due to unknown parallax. It has a 6-year frequency. Okay, I will skip this. So all of that you can actually do in practice using these parameters, using these software packages. There are two ways of doing this. One is to do the full nonlinear timing model and the noise together. So that is sometimes called SPNTA. So there are two packages for doing this called TempoNest and Wheeler-JL. The second way and the more computationally efficient way is to take the linearized timing model. And this is usually sometimes called SPNA. And there are various packages. There are Enterprise 42. This Discovery and Prometheus were developed recently, and they support GPU acceleration. So they are very, very efficient. And I will leave you with this quote from George Hobbes, who so yeah, thank you. And sorry for taking more time.
Got it. That's very important and useful. Questions? We'll take questions. We'll take question number menu.
Oh, okay.
Okay, let's take it from the room first. Questions?
I'm just curious about the effect of the binary orbit noise on the detection statistics or on
Can you repeat that, please?
Yeah, you were talking about the spin, the binary orbit noise. Do we know what the effect of that is on your detection statistics or your pipeline in general, like everything that comes?
I frankly don't know, because it has not been studied in any great detail. So this is actually more of a problem in high energy timing, because some of these pulsars are accreting and they have like ablation and those kinds of behavior. So this has been done more in gamma ray timing, and some of the pulsars in the gamma ray PTA, I believe, has this kind of thing effect. But there are like 4 or 5 pulsars in radio PTAs also that has this kind of effect. I frankly don't know what the effect of that is. And I think if the orbital period falls within the sensitivity band of the PTA, then it will be a problem.
I also have a question in the same context I'm going to ask. So is it also treated as a red noise?
It is. It is not exactly a red noise. So the way it is treated, according to literature, is that you treat the phase of the binary as a Gaussian process, which rather you treat it as the Keplerian post-Keplerian orbit plus some Gaussian process noise. So it is not a Gaussian process in the TOA domain. It is a Gaussian process in the orbital phase. That's the way it is treated. Yeah.
More questions?
Hi, thank you. So I'm fairly new to the world of PTAs, and when I learned about EFAC and EQuad, I was like puzzled. And so from my understanding, it's just like some white noise that maybe we don't fully understand where it's coming from, but somewhere in the telescope backend. Is that something that if we put a lot of time into, we could eliminate and by understanding our observatories really well? And is that even worth our time in terms of sensitivity to a gravitational wave background?
So it makes a difference, I think. So So it is to a large extent determined by the TOA uncertainties. And if we build like better telescopes with like cryogenic cooling or something like that, then we can actually make that smaller. But parallelly, we also have to improve our data reduction and data analysis methods so that like things like, for example, polarization calibration that can like throw off the accuracy of those measurements. So it is both. You need better hardware and also you need better software to get that better.
Thanks for the talk. I really want to know how does polarization miscalibration will affect your TOA uncertainty?
The way I understand it is that the pulsars are some, or at least some pulsars are strongly polarized, polarized objects. And if you don't do your polarization calibration accurately, the different observations may have like slightly different total intensity profiles. So those will lead, those are like small deviations in the shape of the pulsar, which is kind of like pulse jitter in a way, but it is not really intrinsic variations in the pulse profile, but rather the way the rather inaccuracies in the way we are dealing with the polarization. So that I'm not really an expert in this, but there are ways, things like matrix template matching, where you include the full polarization data. That actually has been shown to improve the TOA accuracy to a significant extent.
Thank you.
Hey, should I continue? Oh, so I have a silly question, I think. So for detecting the gravitational wave, so what is the order of timing residual we need? I think in some microsecond.
Yeah,
Okay, so
even without like, if even if you are even if you have like microsecond level precision, I think by having a long enough time span, you can actually actually detect gravitational waves. So that is actually the case for some of the earlier data on all the pulsar timing arrays. So they don't have like sub microsecond precision, they have of the order of microseconds. But like, of course, if we have much better precision, then we can detect it
obviously.
much
So
better.
my question is, up to what extent we should model these noises so that it will increase our detection?
Okay,
what
so
will be
it is not that it is increasing our chances of detection. It is more like it is allowing us to be more confident in what we are detecting. So sometimes if we don't model some of these things, we will get false detections, which is a bigger problem than not detecting at all.
Okay, nice.
Now we'll take online questions.
And there's one question on Zoom. It reads, I was wondering how we choose the number of basis functions in a GP model, and how does that choice affect the recovery of red noise and DM noise parameters? I mean, if we use more or fewer basis functions in the GP setup.
So I am actually not an expert in that, because I have not actually done the harmonic selection. So there have been like different ways of doing this. Some people have done like treated the number of harmonics itself as a sort of parameter to be estimated in a Bayesian way. But I think that is one approach, I think. So another approach is to just use a very large number of basis functions and say that, but then the problem becomes that your like it becomes covariant with pulse jitter and pulse jitter and radiometer noise. So it's a trade-off, I guess. And I don't know, I actually don't know the answer to that question.
Thanks.
More questions in the room?
I think she has a question.
Yes, thank you for the very detailed talk, yeah, especially on the various noise sources. Yeah, I'm wondering that how should we balance the modeling of the noise. We want to avoid overfilling and degeneracy. But at the same time, we have to consider the computational cost. So what's your recommended approach?
I don't think there can be a recommended approach which works for everyone. It depends on the properties of your data. So I think it really helps to have really deep knowledge about all the systems that are going into your data, so that say things like ephemeris noise or clock noise, those really, so those are like, you don't really have to model them all the time. You only have to model them if you think independently of your pulsar timing experiment that there is something wrong with your clock or something wrong with your ephemeris or something like that. So similarly, some of these noise processes actually can be removed without even coming to the TOA domain. Things like even pulse jitter can to some extent be removed at the profile domain, or the scattering can be removed at the baseband domain. So I think an ideal situation would be that whatever we can remove is removed at the appropriate level, and so we have as few sources of noise as possible at the TOA level. So that is, I think, the most computationally, both computationally as well as sort of from a analysis complexity point of view also. That is the right, that is the correct approach. I also want to mention that as we so as we go up the pyramid, the size of that pyramid decreases, right? So that represents the amount of information you have. You have all the information when you have a baseband data, so that some of these signatures that are only present in baseband you can correct. Whereas if you try to do that in TOS, you have much less information, so that your data is constraining that process much less. So from that, my personal opinion, my sort of dream PTA would be one where at each of these levels, noise processes are taken care, and at the TOA level, we only analyze things that are really can only be dealt with at that point.
Yeah, thank you.
More questions?
Thanks for the great talk. I just wanted to ask, do you know if the order of operations in which we process the data to remove all these different things, is that well established? Like, is that well established and well communicated across the community? Are we all doing the same thing in terms of, do we disperse first and frequency scrunch and then arc clean? And
I don't think there is any sort of standard procedure, because I know in PTA, for example, we do our noise or RFI removal at the light curve domain, whereas in some other PTAs this is done in the profile domain. So even something like that, there is no standardization. And this is also sort of dictated by practicalities. So some telescopes don't produce this light curve at all. They only produce the profile in pulsar observation mode. So you don't even have that kind of freedom to choose. So I don't think there can be a uniform procedure, because different telescopes have different different data structures and such. So we not all observations are made equal. Yeah.
Last question? If not, I'll ask, since you said scattering noise is the most nasty one, I think. How do you think we can make use of scintillation studies for that?
Okay, I'm not the right person to answer that question, because I know very little about scintillation studies. So I'm not the right person to answer that question.
Thank you.
But if you can solve it, please do.
Try. All right, so let's thank our speaker again. So